Okay, this is the first section, and if you notice, some of it's kind of already filled in. That's because I did a first take of the video, and then I thought I had made a mistake somewhere, and then I ended up not making a mistake, and so there was like a big pause in the video. So some of it's already filled in, but it's pretty basic stuff here. This is kinematics and dynamics, so we're finally circling back around to the stuff that we did in physics 1. So pretty much everything in here is gonna go pretty quickly, except for some of the stuff that is new for you. Okay, we have our equations here. This is our constant velocity equation. So you have constant velocity, right? Your position is simply going to be your initial position plus your change in position times the time. Change in position is just velocity, right? So we're doing x equals vx naught times time plus the initial x position. These are cases in where you have constant acceleration. This gives you position if you have constant acceleration, so you do have to add that factor of acceleration in there. And then you also have for your velocity, your velocity will be changing over time, so that's why we account for that here. There's another equation for constant acceleration without time. This is what we call the no time equation. This is a really popular one. It's really helpful a lot. This is basically giving you these values without having to involve time. So if you're not given time in the problem, pretty much if you're not given time in the problem, 9 times out of 10, you're gonna have to use this equation right here. Average velocity is simply change in position over change in position over change in time. Change in position is also known as displacement. Okay, and then average acceleration is change in velocity over change in time. Okay, so those are some important relationships to remember. The first problem here, if it doesn't say Jonesy with a boogie bomb, it's the same numbers. Okay. So he launches a boogie bomb straight upward from the roof of a building, 20 meters above the ground. Ball initial speed is 30 meters per second. Use g equals 10. So notice if you throw something straight upward, right? If you throw something straight upward, it's going to hit each height value, each y value twice, right? It hits it once on the way up and then once on the way down. So when it asks us what 2 times is the boogie bomb 60 meters above the ground, that means that when he throws it up, it's going to hit 60 meters at some point, and then it's going to go hit its top, and then it's going to go down. And as it goes down, it'll hit 60 meters again. Okay. So the way that we solve that is we would have to use because the trajectory is, even though it's technically one dimensional, it's kind of also parabolic. So we would just use the equation right here for the constant acceleration for the y direction. And our acceleration this time is g. We have to subtract it because g is going downwards. Okay, so as we throw it up, right, the ball is slowing down, and when it gets to the top, it stops, and then as it goes down, it speeds up. Okay, due to gravity. So then we just plug everything in. So y is the final height that we're looking at. We make it 60. 1/2 times 10 times t squared. That just gets pulled down straight there. Your initial y velocity is 30 meters per second upwards. So I just use positive 30 right there times the time, which we don't know yet. And then the initial position, you're 20 meters above the ground. So I would make this 20. If you wanted to, you could make it 0, but you'd have to add that 20 back in at some point. So it would just make everything a big mess. It's easier just to do the 20 here. So then what you'll notice is that what ends up happening, half of 10 is 5, so I end up getting with negative 5t squared plus 30t minus 40. And the reason, how did I get negative 40 right here? It's because what I did was I took the 60 and subtracted it from both sides to get negative 5t squared plus 30t minus 40 equals 0, okay? And then you can actually factor that out. You can actually factor the 5 out, okay? If you divide the 5 on both sides, okay, then you'll actually see that you can actually condense this. I divided by negative 5 on both sides so that because I don't like leading negatives right here, okay, but I was able to divide by 5 on both sides to get t squared minus 6t plus 8 equals 0, and then that you can actually factor out into t minus 4 and t minus 2, and you would see that to meet this condition that either one of these ones in the parentheses needs to equal 0 to meet this, to satisfy this. So we would say that t is it would be equal to 2 and a 4. And so these are the 2 times that the ball is at 60 meters. Okay. To find the speed, I'm going to say the easiest way to do this is to use is to use the no time equation, because you notice that we're not given time for the whole thing, right? Well, we know the time when it hits 60 meters, right? I don't want to depend on the time here. The reason is because what if I got the time wrong here? Okay, so I'm going to use the no time equation because I don't want to depend on it. And you'll notice that the delta y, this is not going to be from it's not 60. Instead, it's going to be from 20 to 60, which is 40. So that's why I'm substituting 40 for delta y instead, because I go from 20 to 60. I'm already at a height of 20, and I'm just throwing it up to the 60 point. Okay. We want to figure out the speed of the ball when it gets up there. So we're using Vy squared equals -2 parentheses 10 parentheses 40 plus parentheses 30 squared. And then you can actually plug all of that stuff into your calculator, and you would actually end up getting plus or minus 10 meters per second. And the reason why we're saying plus or minus is because you would actually have to square root it, right? You would notice that you would add up everything on the right hand side here. Then you would need to take the square root, and when you square root it, you don't know if the original number, right? Because if you square root it, that means that this was actually 10 squared, and you don't know if the original was positive or negative. But it actually makes sense in the context of the problem, because as it goes up, it should be positive 10 because it's going upward, and then as it comes down, it should be negative 10 because it's going downward. Okay. Okay. The next example is a confusing one. Okay, this next example is kind of crazy because you actually have to break it up into two parts. Okay, so what the problem tells us is that Lara Croft is standing near the top of a high cliff. She drops a rock from rest. She hears the rock strike the bottom 20 seconds later. Speed of sound we are given is 320 meters per second. Acceleration of gravity is 10 meters per second squared. Air resistance is negligible. Okay, great. Just like a normal physics 1 problem. Okay. Um, so to figure this part out, this is actually a kind of a two-part. So we need to figure out first off the full time for the whole thing happening. And the full time for the whole thing happening, there's two things that are occurring in this problem. The first is that the rock is falling to the ground here. So that's the first thing that happens. Then what happens is the sound travels up. So if you think about it, really the total time for the whole thing to happen, what I'm going to call the full time, okay, to get the full time of the whole thing, it would be the time, I'm going to call this T sub f for the time falling, and add to that T sub s for the speed of the sound, or the time that it takes for the sound to go up, and that would give us the total time, which is 20 seconds. Okay, so the full time takes 20 seconds. Well, now we need to figure out the time for falling and the time that the sound takes. Okay, so for the falling, okay, for the time falling, I'm just going to use a the basic free fall equation, okay, which would be y equals 1/2 gt squared, okay. And now what I'm going to do, okay, y is our height, and maybe instead of using y, I should use h, okay, for height, okay. Now what I want to do, this is not just any t squared, this is the time for falling, okay, t falling. Well, 1/2 of g is 10, right? 1/2 of g is going to be 5. So this is h equals 5 t sub f squared, okay? And if we want to get t sub f by itself, okay, you would end up getting root h over 5. Now, why am I getting t sub f by itself? Is because we can actually solve for the height of the cliff using the time values, okay? And I'll show you how we're going to do that. It's a really weird process. Okay, that's for falling. And then for the sound, okay, for the sound, you would have to understand that the height can be found by the velocity of the sound times the time it takes for the sound to travel. So if we figure out how long it takes for the sound to reach the bottom, from the bottom of the cliff to where Lara Croft is standing, okay, then we can multiply that by the velocity to figure out how high, right? If it goes 300, if it goes 320 meters per second, and it takes 1 second, okay, well then it would go 320 meters, right? So that can give us our result, okay? Um, and we know that v sub s is 320, so we can get that h is equal to 320 t sub s. And so when you get t sub s by itself, you're just getting this expression h over 320, which is, that's all you gotta do for that. So now what we gotta do, and this is where things get kind of funky, okay, is now what we're gonna do is we're gonna have to rewrite our full-time equation, okay, rewrite the full-time equation, but with those values that we just got. So what I would do is I would take, okay, T sub f, right? T sub f is this right here. T sub s is this right here. So I'm going to plug those in. Root h over 5, okay, plus h over 320 equals 20. Now, I'm going to spare you the hard part here because you would have to do quadratic formula with this. This would be a complete mess to do. You would have to subtract h over 320 from both sides and then square both sides, use the FOIL on the right-hand side, this cancels out that radical, and then you would have to do some really gnarly quadratic equation with it, and you get some really crazy numbers out of it. But when you solve the whole thing out, you actually should end up seeing that h would be equal to 1280 meters. Okay? That's what you should get. You'd have to factor the whole thing out. You'd have to do the whole thing. You're not going to see anything too crazy like this. This is a really crazy example, but it's good practice, of course, right? Okay. The next example is a segmented motion example. Okay, this is segmented motion now. We briefly, you might have briefly seen it in Physics 1. Okay, it's segmented motion. Okay, segmented motion just means that basically, like your an example might be that like for a moment you have acceleration, then for the next moment you don't. So you have a runner in a 100-meter dash with acceleration of oh, I haven't used this pen yet. Wow, impressive. Okay, a runner in a 100-meter dash has an acceleration of 5 meters per second for the first 10 meters of the dash, then travels the remaining distance with constant velocity. Okay, what is the constant velocity for the remainder of the race? How long did it take for the runner to complete the entire race? Okay, so basically this chart right here, this is like a little timeline of what's happening. We're basically charting the events that have happened. The first section is when the runner is accelerating. Okay, and the last part is constant velocity. Okay, so initially, the runner is going to start the race at a position 0 meters, right? Unless he's a dirty, rotten cheater. He starts the race at 0 seconds because he's a cheater, or he's not a cheater, sorry. And then the velocity should be, she should also start at 0 because he starts from rest, right? I mean, that would make sense conceptually that the runner does not start going some speed unless he's cheating again, okay? What's some other information we can get from here? Okay, so when does he stop accelerating? Well, it says he stops accelerating when he hits the 10-meter mark. Okay, and his acceleration while he's accelerating is 5 meters per second squared. Okay, the change in position from when he starts to where he stops accelerating is 10 meters. Okay, when does he end the race? Well, it's a 100-meter dash, so he should end at the 100 mark. And then the change in distance from 10 to 100 is 90. Okay. And now, oh, and also constant velocity, so he has no acceleration, and that should be everything that we need that we can fill in right off the bat. Okay. Okay, so now we need to spend some time to fill in the blanks. You solve it like a logic puzzle, kind of. Okay. The first part is to get the first delta t. That's what I'm going to do. I'm going to get the first delta t here. Okay. I need to figure out what's the change in time between the starting to when it stops accelerating, when he stops accelerating. Well, I'm just going to use, if I have acceleration, right, constant acceleration, I'm going to use my constant acceleration equation, okay? And I need to have a term of time in there. So I'm going to use 1/2 a t squared because I have no initial velocity, so that term gets canceled out. My initial position is 0, so that term gets canceled out. Okay, plug it all in. X is going to be 10 equals 1/2 the acceleration, which is 5. So 5t squared. And then watch this. You probably don't even need to be a rocket scientist to figure this out because this is 10 equals 2.5 t squared. Okay, well, how many times does 2.5 go into 10? 4 times. What's the square root of that? Oh, it's 2. Okay? So just to be clear, right? This would be 10 divided by 2.5, which gives you 4 equals t squared. And then you should get t is equal to 2 seconds. Okay? So that's your change in time from the beginning to the middle part when he stopped accelerating. So the clock when he stops accelerating should read 2 seconds. Okay? Okay. To get the velocity, and I should have got my orange pen out. Okay? Okay. to get the velocity, okay, um, we can, so this is my second step. Okay, I'm going to get the velocity after accelerating. Okay, so after he accelerates, what's going to be his velocity after he finishes accelerating? Well, v is equal to at plus v naught, and v naught is 0, right? So it would just be v equals 5. He does it for 2 seconds, so he should end up having a speed of 10 meters per second. Okay? Okay, so his velocity at the end is 10 meters per second. Great. Now, because he doesn't have any acceleration, he should still be going 10 meters per second at the end, right? 10 meters per second. Okay? The final step is going to be to find the second delta time. That's the last thing that we're missing. Okay? Okay, to get the second delta time, all we have to do is use x equals, there's actually two ways to do it. You could do x equals v average times t. That's actually what I'm going to do, is do v avg times t. Okay? Well, the average velocity here, okay, average velocity here is 10, because you start at 10, end at 10, so your average velocity is 10, okay? 10. The time, we don't know, and I'm so sorry, the position, we do know, the change in position, he goes 90 meters, right? Okay, so there you go. 90 equals 10 times t, and t, you should be able to see, is equal to 9 seconds, okay? So there's that. So it should be 9 seconds, and then the total time should be 11 seconds. Okay, so when you map this out, when you graph it out, okay, here's what it should kind of look like. So for the first segment, you have acceleration, which means that your position function actually needs to be concave up. It's positive acceleration. So it needs to go from 0 to 10. Where is it? 10. Okay, and it's going to have a little bit of concave upness here, and I'm trying to make it like obvious. Can you see that? Okay, and then when it goes, and then it ends up at a 100 at 11. So there's 11 right here, ends up at 111. This is going to be a constant velocity. So, oh, I drew that horribly. Can you see that? I drew that horribly. Always use a ruler for your straight lines. Okay, there you go. Okay, there you go. Ignore that little hanging one right there. Okay. For the velocity, again, it's going to look, so right now it's steadily increasing from 0 to 2 seconds up to a maximum of 10. Okay. So that's going to be a straight line because the velocity is constant, or the acceleration is constant, the change is constant, and then the velocity becomes constant until the end of time. So the line just becomes a flat line. Okay. And then finally, the acceleration, well, he's only got acceleration for the first part, and it's just 5 meters per second the whole time for the first 2 seconds. But then after that, it drops down to 0, and we never get any more acceleration ever again. So it would just be a flat line at the last interval, okay? Okay, I love this problem because it says a person traveling 40 meters per second in a car encounters a reason to make an emergency stop. It doesn't tell us why he's making that emergency stop, but it says that he has a reason to do so, okay? It takes the person 2 seconds while traveling with constant velocity to react and apply the brakes. Then the car comes to rest with acceleration of magnitude 8 meters per second squared. Okay, so the first segment here is going to be reacting, and the second segment is going to be braking. Okay, so when you do this, okay, when you solve something like this, let me fill in the important information that we've already gotten so far. Traveling 40 meters per second, that's initial velocity. Takes 2 seconds to react, so it takes 2 seconds, 2 seconds, okay. And he should still, he's going, so he goes at constant velocity, so it should be 40 meters per second there in the middle velocity as well, okay. If he's going constant, then there's no acceleration, okay. Then let's see. When he brakes, he has an acceleration with magnitude 8 meters per second, so it's actually negative 8 meters per second squared because it's slowing him down. And at the end, he should be at rest, which is 0 meters per second. Okay? Am I missing anything? I don't think I'm missing anything there. Oh, his initial position, let's call it 0 meters. The initial time, let's call that 0 seconds. Okay, just let's make life easy on us, okay? Okay, so the first step here, what I'm going to do is get the second delta t, and you can actually, I guess, solve any of these in any order that you want. Like, so do whatever works best for you. Okay. And to do that, I'm going to do v equals a t plus v naught. Okay. Um, our final velocity, right? Our final velocity, so we're doing the second delta t, so we're doing for just this segment right here. Okay. Our final velocity should be 0. The acceleration should be negative 8 t, and then plus the v naught, which is 40. Okay. If you solve that out, you'll see that t should be equal to 5 seconds, okay? And you can probably tell that because you're thinking, okay, move the 8t to the other side, okay? And then there you go, okay? So then the final time, the final time interval should be 5 seconds, okay? And then let's see, if we're at 2 seconds here, then it would be the change in 5 would give us 7 seconds. Okay, so he stopped. It takes 7 seconds for him to completely stop, which is a pretty long time, okay? The next thing that we're going to do is get the second delta x. Okay, we need to figure out this delta x right here. How are we going to do that? Well, I'm just going to do delta x equals VAVG. Okay, delta t. Okay, well the average velocity is 20 because it goes because 0 plus 40 divided by 2. That's the number of values that I'm working with. Is 20. Okay, so I should get delta x is equal to 20 times the time, which is 5 seconds. So it should be 100 meters. Okay, so he ends up at the 100 meter mark. He changes 100 meters here. Okay. So we don't know where he ends up in the middle part. Okay. Um, okay, so there's that. And then we need to figure out the first delta x now. And you can really do this in any order as long as you have the relevant information. Okay, get first delta x. Okay. How do we get the first delta x? Well, let's see. I'm going to do the same thing. Delta x equals VAVG times time. I don't really like using V average, but it works out just fine here. Okay. Average velocity for the first segment. Wait, you start at 40, you end at 40, so your average is just 40, right? Okay. And the time it takes for you to do that is 2 seconds. Okay, so I travel 80 meters? Okay. Boom. 80 meters. So I continue. I go 80 meters here. I end up at 80 meters here. Okay, so if I'm at 80 meters and I travel another 100, then I should actually have 180 meters right there. Okay. Let's look at what those graphs look like. So for the first part, there's no acceleration, so it should be linear on the position graph. It should be a straight line. Okay. And let's see, we end up at 80. Okay, so then at 80, 80 at 2 seconds. Okay. And then for the second segment, you have a deceleration, so it should be concave down, and you end up at 180 at 7 seconds. Okay? So then it should be a concave down kind of function. It's going to look kind of ugly. Okay? Okay, for the velocity, right? Well, you start out at 40, and then you gradually go to rest until you hit 7. At 7, you hit rest, and so now, okay? And then your acceleration, you notice that you don't have an acceleration for the first two, but then when you apply the brakes, you get a -8 acceleration. Okay? Okay, there's that. Now let's do the last problem is this rocket problem here. Okay? A rocket initially on the ground begins firing its engines at time t equals 0. Rockets fire for 2 seconds, giving the rocket upward acceleration of 30 meters per second squared. Rocket engines then shut off, and rocket enters free fall motion. Use g equals 10. Okay. So it tells us what each of the segments represent here, which is very nice of them to do. Okay. Let's fill in the important information. If the rocket engine starts firing, you're at 0. Okay, you're at 0 meters. The timer starts at 0 seconds. You're initially trying to go from rest, so you're at 0 meters per second. Okay. The rockets fire for 2 seconds. Okay, so from the time between they start to where they end, it's 2 seconds. Okay. Giving the rocket upward acceleration of 30 meters per second. Okay, so 30 meters per second squared is our acceleration while the rockets are firing. Okay. So our time at the end should be 2 seconds. Okay. When the rocket engines shut off, okay, now the rocket enters free fall, so the acceleration should be negative 10 meters per second. Okay. Squared, sorry, meters per second squared. Okay. We don't know anything else about that. And then the rocket reaches the maximum height. We should know that at the maximum height, the velocity should be 0 meters per second, right? Because if it's at the top, the velocity momentarily becomes 0 before changing directions. Okay. And then you would do, let's see, so then the A, okay, acceleration as it's falling, it's still negative 10. Okay. And then when it hits the ground, it should be back to 0 meters. So it's going to be a really funky ride. Okay. Okay. It wants us to elaborate the steps um, at the bottom, okay, and that's fine, okay. Um, so it wants me to elaborate the steps down here. Okay, so the first thing that I want to do is get delta y while firing. Okay, so while the rockets are firing, okay, how high up does it go? Well, I'm going to use y equals 1/2 at squared. Boom. Calculate that. Plug everything in. Y equals 1/2 the acceleration of the rocket is 30, and then the time that it fires for is 2 seconds. Okay, and do you end up getting 60 meters per second? You should end up getting 60 meters per second. Or sorry, not 60 meters per second, 60 meters. Okay, because it's a distance. Okay, and then so I'm going to go back up here, and it's going to say the change in distance is 60 meters. So I end up at 60 meters above the ground there. Okay. Okay. Now, the next part that we can solve for, okay, is step 2, get the velocity after firing. Okay? So how fast is the rocket going when the engines turn off? Okay, well we can figure that out. V equals AT plus V naught. Well, V naught is 0, so we don't really need to worry about that. Okay, so that would be V equals the acceleration, which is 30, and the time that it happens is 2. So it should be 60. Okay, it's 60 meters per second. So he should be going 60 meters per second when he hits the top, or when the rockets stop firing. Okay. Now, you can actually automatically figure out from here the time. Okay. You can automatically figure out the change in time here, because if you notice, your acceleration is negative 10 meters per second squared, which means every second you lose 10 meters per second squared of speed. And how many seconds does it take? So if you lose 10 meters per second every second, and you have 60 meters per second, how many seconds does it take to get to 0? It should take 6, right? So then 6 seconds, because it takes 6 seconds to lose 60 meters per second. Okay? That's how we're able to get there. Okay? Okay. Oh, sorry. The change in time is 6 seconds, and then our actual time would be 8. Okay? Actual change in time is 8 seconds. Okay? Because we have to account for that too earlier. Okay. Let's see. So we need to figure out the height that which the rocket goes. Okay. We need to figure out the height that the rocket goes. And the way that I'm going to do that, okay, we need to figure out the maximum height that the rocket goes to, is that when the engine stops firing, we know it's at 60. Okay. So we would just have to use this equation. Okay. Y equals Vy naught T plus, minus 1/2 GT squared. Okay, so I'm going to use that equation right there. 1/2 G is 5, so I'm just going to plug in all the numbers now. Okay, this is going. Our initial y velocity is 60 meters per second. We do this for 6 seconds. Okay, and then we subtract the 5 times t squared. Okay, and that would be 5. It takes 6 seconds to do the whole thing, okay? And then when you subtract the whole thing, you should end up getting about 180, okay? So the highest point that it reaches is 180 meters, okay? So the change from 60 to 180 is 120, okay? Okay. Um, oh, sorry, this should be 240 right here because the change is we found out the change is 180. 180 is the change. This is 240. Okay. Wow, I'm really messing up here. I'm so tired. I don't know why this is messing up. Okay. 180 meters and 160. Okay. So there's that. Now the last thing we need to figure out is the delta t, and also you can figure out the delta y from it, right? Because if it starts at 240 and drops down to 0, then that means it dropped 240 meters. Okay. Okay, and the last part that we need to solve for is simply going to be the final time. Okay, so let me show you how we can get that. Okay. Okay, you get the final or final delta t. Okay, and how can I get the final delta t? Well, let's see. The easiest way to do it for me, okay, in my opinion, is going to be use just your normal constant acceleration equation, 1/2 gt squared, or I guess it would be negative, right? Negative 1/2 gt squared plus vy naught t plus y naught, except that vy naught t is going to become 0 because you don't have any initial y velocity. Plug all the numbers in. Our final height should be 0 equals 1/2 g, so that'd be negative 5 t squared, okay, plus y naught, okay, our initial height, which is just going to be the 240, okay? You would figure that part out. You would solve for t, which is pretty easy. You add 5t squared to both sides, divide by 5, and then square root the whole thing, and you should end up getting that t squared will be equal to 48, okay, to 48, which means that if you take the square root of that, you would actually just get t equals root 48, which I'm fine with. That's approximately 7. Oh, that's a 9. Why did I write a 9? That's approximately 7, okay? Approximately 7, which is perfectly fine, okay? So I'm going to say that the change in time, the final change in time, is, root 48, which is about equal to 7 seconds, okay? And then the time, right? The final time, it should be about, the final time, it's going to be about 15 seconds, right? If we do 8 plus 7, that gives us 15. Okay. And the last part to figure out is the velocity, which isn't that bad. Okay. Um, all you'd have to do is just use Vy equals the acceleration times the time. Okay, and your acceleration is -10. The time it takes is about 7 seconds. So you would get about, and not perfect, but you'd get about 70 seconds. Okay, or sorry, 70 meters per second. So then the final one is about 70 meters per second. And I'm writing the about, like the kind of equal to part, because it's not perfect. Okay. Okay, so if we graph this, what's that going to look like? Well, for the first segment, up until what, 2 seconds? Okay. Well, actually, for the first segment, right? It's going to be concave up, and it's going to hit so at 60. So here's 2, here's 50, here's 60. Okay, so it should be concave up here. Now what's happening is here the rocket stopped firing, so the acceleration is now negative, so it should actually be concave down. So we're going to change concavity here to concave down. Okay, so for the second segment, it's going to take 2 seconds. It should accelerate uniformly in the negative direction. Okay. So let's see. This is position versus time, so it's said it increases to 60. Now we're going from 60 to 240. 240 at 8 seconds. Okay, let's figure that part out. 240. And this whole part, because it's accelerating downward, will be concave down. So it's going to look kind of something like this. It's pretty good for not having like a ruler or anything. Okay. And then for the last part of it, it's still accelerating downwards, so it's still going to be concave down. So it'll eventually crash land back at 15 seconds. So it'll probably look something kind of like this. Okay. I keep messing up my lines because I don't have my rulers or anything like that. And then for the velocity graph, you should notice that for the beginning, while the rockets are firing, it's steadily increasing. But then after that, the velocity decreases because it's now essentially in free fall, right? So the velocity at at 2 seconds. Okay, the velocity at 2 seconds is 60 meters per second. Okay, so here's one, here's two. Okay, and then 60 is right about up here. So what's going to happen is it starts at 0 and then gets up to 60, and it shouldn't be curved at all. If it looks like I did, then I apologize, okay? And then it'll end up at 0, or sorry, it'll end up at a different velocity. Should actually, yeah, it should end up at a negative velocity at 10, okay? We just know that it hits 0 velocity at at time 8, so 6, 7, 8. So we know it hits right there. And from there, you could just understand, okay, the acceleration is the same. So what I'm going to do is I'm just going to draw a flat line continuing through. Okay, that's fine. Okay. So this is how your graph should look. Okay. Finally, how do we find the maximum height? And how can we get that from the velocity time graph? All you'd have to do, and this is like super, super simple, okay? All you have to do is find where v is equal to 0. That's it. That's all you gotta do for that. Okay. All right. I think that's all section 1. Yeah, that's all section 1. We're moving on to graphs next. Okay, have fun. Go boss it up.